We've spent a lot of time on how batch jobs process data. Now let's ask the question most people forget: what is the output, and who uses it? Here's the key insight. Batch job output is never served directly to end users. A user never waits for a MapReduce job to finish before seeing a page. Instead, batch jobs produce derived datasets, pre-computed results that other systems can then serve with low latency. Think about the distinction between transaction processing and analytics. OLTP systems look up small numbers of records by key using indexes, they serve individual user requests. Analytics queries scan large numbers of records and compute aggregates, they produce reports. Batch processing is closer to analytics, but it's not the same thing. A workflow of MapReduce jobs is not a SQL query over a data warehouse. The output of a batch job is often not a report, but a structure, a search index, a machine learning model, a recommendation database, a pre-computed key-value store. Consider how Google originally built its search index. Their original use of MapReduce was to build indexes for their search engine, implemented as a workflow of 5 to 10 MapReduce jobs. Although Google later moved away from MapReduce for this purpose, Hadoop MapReduce remains a good way to build indexes for Lucene and Solr today. Here's how it works in practice. A full-text search index like Lucene is a file, the term dictionary, in which you can look up a keyword and find all document IDs containing that keyword, called the postings list. The mappers partition the set of documents, each reducer builds the index for its partition, and the index files are written to HDFS. These segment files are immutable once written. They can be bulk loaded directly into Elasticsearch or Solr. If the set of index documents changes, you can rerun the entire indexing workflow and replace the old index files. Documents in, index files out, simple to reason about. Search indexes are one type of batch output. Another common type is a key-value store, a database that the web application can query at runtime. Imagine you're building a recommendation system. The output is a database queryable by user ID to get suggested friends, or by product ID to get related products. This database needs to be served to the web application handling user requests, which is separate from the Hadoop cluster. Here's where most teams make a costly mistake. The tempting approach: write directly from your MapReduce job to the production database, one record at a time using the database client library from inside a mapper or reducer. The book explains why this is a bad idea. First, making a network request for every single record is orders of magnitude slower than normal batch throughput. Even with batching, performance suffers. Second, many mappers and reducers run in parallel. If all of them write concurrently to the same database, with the rate expected of a batch process, that database can easily be overwhelmed and its performance for queries, which real users are waiting on, will suffer. Third, MapReduce provides a clean all-or-nothing guarantee: if the job succeeds, every task ran exactly once. But writing to an external system from inside a job creates side effects that cannot be hidden. Partially completed jobs become visible to other systems. The much better solution: build the key-value store as a file inside the batch job, write it to the output directory in HDFS, and then bulk load it into the serving layer. Key-value stores like Voldemort, Terrapin, ElephantDB, and HBase support building database files in MapReduce jobs and bulk loading them. Voldemort keeps serving the old data files while new ones are copied, then atomically switches over when copying is complete. If anything goes wrong, it falls back to the old files. Building these database files is a natural fit for MapReduce. Extracting a key and sorting by that key is already most of the work needed to build an index. When the MapReduce paper was published in 2004, it was, in some sense, not at all new. All the processing and parallel join algorithms in MapReduce had already been implemented in massively parallel processing databases, MPP databases, more than a decade earlier. Pioneers included the Gamma Database Machine, Teradata, and Tandem Nonstop SQL. So what was the difference? Why did Hadoop take off? The biggest architectural difference is about storage. MPP databases require you to structure data according to a particular schema before you can query it. Files in HDFS are just byte sequences. They can contain database records, text, images, videos, sensor readings, feature vectors, genome sequences, or anything else. To put it bluntly, Hadoop opened up the possibility of indiscriminately dumping data into HDFS, and only later figuring out how to process it. MPP databases require careful upfront modeling and schema design before you can even import data. This approach has been called the sushi principle: raw data is better. Simply making data available quickly, even in a quirky, difficult-to-use raw format, is often more valuable than trying to decide on the ideal data model upfront. The interpretation of the data becomes the consumer's problem, what's called schema on read. The second difference is processing models. MPP databases are monolithic, tightly integrated systems optimized for SQL queries. They're great for business analytics tools like Tableau. But not all processing can be expressed as SQL. Building machine learning models, performing full-text search, doing image analysis, these require writing code, not queries. MapReduce gave engineers the ability to run their own code over large datasets. And because operators are general purpose, different teams can run different processing models, SQL via Hive, machine learning, graph processing, all on the same HDFS cluster. The third difference is fault tolerance. MPP databases abort the entire query if a node crashes and retry automatically, acceptable for queries running seconds to minutes. MapReduce tolerates failures at the granularity of individual tasks, which matters when jobs run for hours with a 5% per task termination risk at Google. Both approaches have merit. The book's point is that they make different trade-offs, not that one is universally better.